Thank you. Good morning, everybody. Happy to be here. Before starting, so basically, those who know Dispelix and have been us presenting before, so we have been very technical. So I thought today I start a little bit from different perspectives. So I guarantee a few sentences of technical stuff as well, but a bit of how we approach this whole AR thing from our side. And who we are actually, what we do. So Dispelix is a designer and fabless manufacturer of waveguide see-through displays. We use this so-called refractive optics or surface relief type of creating solutions for augmented reality displays. The company was founded in 2015. So we are 7 years old, more or less today. We are 140 employees located in Finland, so headquarters. We also have offices in US and China. We have been raising decent funding to the date and kind of pushing forward on this AR display. And after all, let's start with this technical stuff. So what is waveguide display for us? Those who followed the previous presentation, so Alex was also talking about waveguides. Now it is a little bit different. So the key thing here, we have a couple of squares and circles here. So what we do, so we have a light input from a miniaturized projector. You can think about something like a LED illuminated LCOS panel or DLP panel or micro LED projector or laser beam scanning projector. So it doesn't really matter. So basically you have a small projector. And then, of course, what you would like to do for that is couple that projector to the glass waveguide lens of the eyeglass and transfer the image from the projector to user's eye. And in order to get it visible for many of us, so you basically want to do, how does it work here? So you want to multiply the pupil, so basically the image, so that you can see it through a virtual window which is large enough so that one glasses can be used by several people, different eye pupil distance, and you still see the full image. And for that, we use different type of approaches with guiding the light with diffractive optics. Okay, so this is the key principle of our technology. And just to kind of give you an idea what the diffractive optics is, if you are not familiar, so basically we have the backbone, which is basically some glass, and then a very simple example here, so it is some dielectric material which is modulated in this type of simple binary lines and gaps, or there is some organic material which is done similarly. And basically these type of diffractive structures will guide the light inside the eyeglass lens. Okay, the patterns you do might be very complex depending on the solution. Okay, and then we come to the topic of today. So if you think, how many of you have used any of AR displays available today? Hands up. Tested, not used, tested at least few of them. Have you seen? Everybody have seen somewhere online. So let's take your right hands up. Okay, so how comfortable? Everybody, hands up. From fist to 5. Fist being I cannot go outside to the Lisbon city wearing those. 5, I'm going. So what is your opinion? 1, 2, 3, now. Okay. Some are very comfortable, some are not at all. So let's see what we can do from Dispelix point of view to drive this so that you would be everybody happy to go outside and see. So there are few key things, rather simple things, but very complicated when you try to integrate those things on the device level. Of course, we are only doing this display element or lens element, but we have to think about the whole device when we are designing this. So one thing, we have to have a prescription somehow integrated. So there are like 4 billion people globally needing prescription, which is almost as many as internet users. So kind of good hint that you need to integrate it somehow. And if you want to do a very nice looking AR device, so you cannot have a separate glasses underneath and then put these AR glasses on the top. Of course, you could maybe use contact lenses, but if you are eyeglass user, so do you want to use contact lenses? Maybe, maybe not. Then you have to have certain design elements. So usually eyeglasses have sort of tilt on the lenses, so pantoscopic tilt or frame wrap. So basically enable the aesthetic form of the device. Then you have to have a simple temple arm. So basically you don't want to be like a racing horse with something on the side of your eyes. Then in the end, you do not like to use a device that looks like a TV monitor on your head. So basically, having a device that is display but doesn't look like a display. So this is a big challenge, and you see in a minute why. So today, because I have I'm lucky, and I also give a talk tomorrow, so you can also learn something new tomorrow at the same time at the main stage. So I will cover some of these topics tomorrow, but today let's focus on these. How does display doesn't look like a display? And here we have 2 examples, our concept demonstrations. So it is not full device, it is demonstrating the concept of display concept. So basically integrated projector, integrated waveguide display. If you like, you can come to our booth and test this out. At the end you see the booth number. I don't remember it from my heart right now. You see it. So this one is based on LED illuminated LCOS display, and this is based on laser beam scanning display. Okay. So what are the challenges then? One thing is some sort of things that are maybe distracting. So if you like to go around to the cafe in Lisbon and wear these glasses for some purpose, so do you accept this type of features? Nothing against these devices. I have seen them in practice. They look great from image point of view, but something could be done better from let's say, aesthetic perspective. The other challenge is the light leakage. Again, another great device here, Microsoft HoloLens, but this is kind of what looking like a display, so I think this is not very convincing to wear this type of thing when you go around. It is 2 things here. One is, okay, how does it aesthetically look outside? And the other thing, okay, you cannot see your friend's eye when you are discussing, and one is wearing and using those at the same time. And then the other thing is the limited privacy. So basically, when light comes out, so there is chance that you also can see the information that is not meant for you. Good. So what kind of approaches we have taken in Dispelix? So here are this demonstration device. Again, you can come by our booth and see it. So we have designed our solutions so that we can, first of all, minimize this optics visibility. It is requiring some trade-offs, but currently we have, in my mind at least, we have been doing a good job, and the only thing that is currently revealing the visibility of optical structures is this minor diffraction you can see at some viewing angles, but it's quite little. And if you are kind of a user, so basically this is what you see, so you almost see no distracting features in your field of vision. So you can maybe, if you are very careful, you can see this rectangular box there, which is basically where the image comes out when you are wearing the glasses. And here the creating D0 means that, okay, the transmission of the creating area is matched with the transmittance of the substrate, and then you cannot see it. If you start to look it from the angle, then you may maybe see it, but obviously when you are wearing the glasses, so you are looking through them. So that is the thing from a user point of view. Okay. Then the light leakage. So basically this TV thing on your face. So here is a very simple solution. This is helping already a lot, at least for the how does the display look like when you are around and others are looking at you. So basically we redirect the world side leakage out from the let's say where it can be visible. In this case we redirect it down, and more specifically here like a 16 degrees down. So it is already kind of pointing to this little TV on my front instead of you. This is kind of a bit of a cheating trick, but it actually works very well. So here is one of my colleagues. She is looking at through the device, something content on coming on, so you can see very, very low glow of bluish light coming out to you, but nothing else. And this is kind of social perspective. So if you are using these glasses with others, and your thing is to interact with real people, so then of course this is what you want to see, and not this thing. Okay. Then the other thing, okay, how much light in general comes to the world side, that's more challenging problem. We are working hard in normal case using this kind of diffractive gratings. Binary means that, okay, you have this block and gap of these grating lines I showed you in the very first slides. Okay, so 50% goes to the eye first, 50% goes to the world side. Okay, means basically that a lot of light is lost and kind of wasted. 50% is wasted already by that one thing here. Okay, it is though possible to go with monochrome, basically single color, green for example, solution. You can go down to 1%. So basically almost every light goes to the user instead of the world side. But of course, if you would like to kind of this high fidelity image, so you are not maybe happy with the monochrome solution, in some use cases might be just fine, but you probably would like to have a full color system, so then let's say achievable level would be 10% to the world and then 90% to the eye. This is, however, kind of a challenge we are currently working on. So it is quite a bit of more complex than this simpler stuff. So there are trade-offs between light leakage performance and manufacturability, or let's say in general the solution complexity. But I think this is the way forward and what people want to see in the industry and what we are really working on and finding the solution. Okay, then the second requirement, safety. We are now happy we got the nice looking glasses without disturbing things glowing out from your head. So then you want to be sure it is safe. There are many things to consider. Eye safety, maybe the first and the foremost, because you are wearing these in the face. There's already a regulation that is you have to be taken care of, which is basically this mechanical durability. There's also some regulation for the light intensity. Not that big a deal with LED illuminated systems, and the diffractive optics in general is not the most efficient from power point of view. For example, this previous presentation, so you got 50% efficiency for the waveguide part, so we are way out from that, but you get these other benefits. But for the laser beam scanning, okay, this is the first question everybody are asking. If you are shining the laser to your eye, how dangerous that can be? Okay, it is a bit of consideration, but basically there are already solutions outside AR that you are shining the laser to your eye. But indeed, you have to take some precautions and do some, let's say, feedback loop. Okay, if something breaks, your laser beam scanning mirror stops. So what happens then? You cannot burn your eye. Or if your waveguide will break at some point, so what happens then? So it is this kind of, let's say, integration challenge that needs to be worked. There are great solutions out there. Obviously, nothing is on a consumer level today, but let's say I see it is something we have to pay attention, but this is not kind of any kind of showstopper here. And also, if you think about this first light, how the waveguide works, so we get the input light, one spot, and then we multiply it everywhere over this our virtual window. So then you already balance quite a bit of the light intensity. Okay, and second thing is safety, user safety when you actually use those glasses in some surroundings. So obviously, how I see AR glasses to be used in future, so you go around. You are not static, cable to the wall or something else, your computer, but you really want to go outside and everywhere. So basically, avoid this tunnel vision. You see what is happening here and here. You also have a real-time see-through. Okay, this is if you have been following closely. So now a lot of companies are launching these pass-through VR devices. So basically, you have the real world through the video input, and then you have they are decent. You get a little lag, but in some cases, this little lag is too much. And on those devices, you also have this. You are covered, so you cannot see your sides. But in our mind, the key thing is this real-time, real see-through everywhere. Also through the display and on sides. All right. Again, I cover some of these tomorrow. But let's take a look on this mechanical durability. So here on the left, this is what you don't want to happen. Oh, your eyes don't like it. But on the right-hand side, same waveguide, little bit enhanced capsulation, so it will survive. Okay, and this is another thing. If you go back to this form factor stuff, so okay, how you can make this in a very thin, lightweight form, so that you can actually integrate this in the eyeglasses without need to put a lot of stuff around it. Good. And as said, tomorrow 10:35 at main stage, another talk from Dispelix, little bit more insights. Also, you can come to our booth and now I don't even see myself what is the 128. So booth 128, so you can come by and talk with us. We have plenty of folks there, engineers, sales guys, marketing guys, myself, CEO coming today, so whoever you want to talk, come by. Also nearby, actually behind our booth, we have a Laser Alliance booth, so Dispelix is also one of the founding members of Laser Alliance. It is a alliance for like-minded companies working around this laser beam scanning technology. So we have, let's say, these core technology companies, we have material companies, manufacturing companies, ODMs, and some others. So you can also come by and talk with alliance people there. And then we got a couple of partners presenting here, like Color Chip and Augmented. They are working on these laser beam scanning technologies. You can find their booth as well nearby us. So welcome. And any question? We have a couple of minutes left.
How big are the diffracting element features? Maybe not just in size, but in pitch, and if there is any wavelength dependence, especially between red and blue.
Yes, of course. This is everything waveguide dependency. So basically, you control the propagation based on the wavelength. So let's say the size scale is something like let's say few tens of nanometers are the smallest. You go from some hundreds of nanometers, so that's your scale in feature size. And then your periodicity is something below half a micron, so a few hundred nanometers range. And basically, then these are wisely arranged on the lens surface so that you get your desired output. And yeah, of course, it is design point of view, so this is kind of big optimization problem, and we are running it with supercomputers and very special optimization methods.
And what is the efficiency between the incident power and power redirected in light?
Yeah, so we like to talk about in nits per lumen. So if you got a X number of lumens from your projector, so let's say 1 lumen, very small projector, you have very little output, 1 lumen. So how many nits to user's eye you get? And in this case, you are moving somewhere from 300 to 800 range.
Jussi, thanks for the great talk. 2 questions actually. You introduced this 8-degree tilt. Is this a special design, so you always have to mount the waveguide under 8 degree?
No, it is not kind of specific, but you have to think about from end device point of view, because this is giving you some restriction. Okay, what is your input angle from projector? So what is the optical angle there? And what is the desired direction of the image? So is it coming from horizontal level, a little bit below, a little bit up? So you have to think about this from end device point of view.
Thanks. And the second question regarding the last slide where you introduced the crash scenario. How did you do this? How did you improve it? Is it by adding a special cover class on top?
Yeah, in this case it was improved by a special cover class solution.
Glass or plastic?
Plastic in this case.
So normally waveguides, they have problems of field during the manufacturing. So are you able to have very low cost for consumer market?
Yeah, of course, this is the big question today, how this will be manufactured. So we are working now, or let's say we have publicly announced, we are working with 2 manufacturers, Applied Materials and AAC Technologies. So we are in very close joint collaboration to developing the approach for manufacturability. I personally believe that we have a good direction with, let's say, this early market. It is most likely a little bit more expensive than you could wish for a tens of million scale, but again, it is also based on these same semiconductor manufacturing processes which require the scaling. So basically, we see the direction is so that it will be allowed the consumer scale also from the cost perspective.
Other questions? I have a question. Do you see any potential to be able to add in an eye tracking device to these types of
Yeah, of course, kind of eye tracking is something you can integrate around, or many things you can actually integrate around this, but eye tracking being one, and I would say it has also benefit from, let's say, the image point of view. How is it used now in HoloLens or Magic Leap devices? So you basically use, from image point of view, you have all the other use as well, but from image point of view, you can kind of automatically check your eye pupil positions, and then you optimize the image for individual user automatically.
I have another question, which is some other use cases that you see these types of AR lenses being used in. Do you have any other? You talked about walking around and being able to see your world, but yeah. Do you have other areas that you'd like to see them as well?
Yeah, I think this consumer space is less developed. So okay, what is really the use case you would like to use this? But of course, from the industrial point of view, whatever is requiring this lightweight device, basically you need to wear the device for a longer time. So then I think this type of approach we are promoting should be the right way to go. So it can be basically, let's say, more or less whatever. We have not so much focused on the use case area, but enabling this, let's say, displays for application where you can be flexible on your position, you can move, you can see, and you can really be lightweight.
Last chance. Any other questions? All right. Oh, we got one. Hold on.
I can just ask, what's the weight of the lens?
Weight? Yeah, okay. So we have this couple of options. So starting from 3 grams to, say, 3 to 8 grams in that range for the waveguide only. Then, of course, if you want to integrate some of these, let's say, prescription, more cover glass or whatever it is, so then it's building up. But let's say you can meet this, let's say, normal eyeglass weight between like a 7 grams, 6-7 grams per lens for this kind of devices.
All right, let's give Jussi one more round of applause.